Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to talk about rationalizing denominators as a review for those who are in college algebra. Now, rationalizing denominators is a subject or a topic within mathematics that you learn from early on in math. So you learn this maybe in an elementary algebra class. Somebody gives you something like 1 over 1 minus the square root of 2, or you might have a fraction or a rational expression that involves maybe some variables, right? 1 over the square root of x minus the square root of y. And you're asked to rationalize the denominator. Now, a couple things to note here. One, you're not always going to have to rationalize denominators. In fact, sometimes we have to rationalize numerators. But even then, there are some instances where rationalizing denominators just doesn't make sense. So in general, if the denominator only has a single term, well, I don't even bother rationalizing. There's no point in rationalizing. For example, if somebody handed you a very popular fraction in trigonometry, which is 1 over the square root of 2, there really is no need to rationalize that denominator. However, people do it all the time. They kind of force students to do that, and I'll showcase how that's done. However, there's really no need to do it if your denominator has a single term. I just won't do it in general. The third thing I want to mention here is that once you've determined to rationalize whether it's a numerator or a denominator, a second consideration of distribution comes into play. This is a little easier to showcase when we start getting into rationalizing whether it's numerators or denominators. But just to let you know, that's going to be a consideration of ours as we move forward. So let's go ahead and take a look at this how-to. And I note up here, before we jump into our first example, let's recall a few tactics that will be helpful. And then I mentioned that more tactics will be found in your textbook. I'm specifically referring to the textbook that I use, but any textbook in mathematics that you use will have their own list of tactics of how to tackle rationalizing denominators. But in this case, I'm really speaking about the OpenStax Algebra and Trigonometry textbook, but this works for all textbooks. Anyhow, given a radical expression requiring addition or subtraction of roots, that would be something like these two right here. There's an addition or subtraction, at least in this one right here. There's subtraction of radicals, right? So we first have to simplify those statements. And then after we're done simplifying those, then we dive into rationalizing denominators. So this how-to here is really to remind us that to follow the order of operations, essentially. So when you're given a fraction and you're asked to kind of simplify the statement, maybe rationalize the denominator or something like that, you're going to start by focusing in on the numerator, cleaning that up as much as possible, and then focusing in on the denominator and cleaning that up as much as possible. And then once you have those two projects done, then you go to rationalizing numerators or denominators, in this case, denominators. But that's just a heads up that you really want to simplify things as much as possible before diving into rationalizing. And that's essentially what this is saying. Okay, simplify each radical expression. Just gonna go ahead and grab my highlighter. And then add or subtract like expressions, just like you would in most of mathematics. Then once you're done with that, you move on to actually rationalizing the denominator. And to rationalize the denominator, we have a how-to for that as well. However, just to let you know that the word denominator here is interchangeable for the word numerator. So if you were asked to rationalize a numerator, it's basically the same steps that we're showcasing here. Multiply both the numerator and denominator by the conjugate of whatever you're trying to rationalize, in this case, the denominator. So you'd multiply both numerator and denominator of your given fraction by the conjugate of that denominator, and then you would simplify. So let's go ahead and just take as an example the one example I gave earlier, this 1 over the square root of x. I think it was a minus square root of y. I was just making that up. So if you were asked to rationalize this denominator and simplify, you would start by grabbing that entire numerator and simplifying it. Well, 1 is just a single constant. It's already simplified. Then you would look into the denominator and you'd say, okay, how am I going to simplify that? Again, those are fractions, or sorry, those terms will never be like. So there's no point in even trying to get those two together. You're pretty much stuck. The numerator is simplified, the denominator is simplified. So now what we do is we multiply this fraction by the number 1. And I'm going to actually write it that way. I'm going to multiply this by the number 1. The reason why I want to start by saying I'm multiplying by the number 1 is we cannot change the value of this fraction. We were handed this fraction and told you have to work only with that fraction. And so we cannot technically change its magnitude, or in other words, its size. Let's just pretend that this fraction has a size of 5, whatever that means. Well, you can't just magically change it to a size of 25. You have to keep it the same size the entire time. And that is done in mathematics by multiplying by the number 1. However, the number 1 we're going to multiply by is a very special form of the number 1. It is the conjugate of that denominator over the conjugate of that denominator. That is, go ahead and just put parentheses here. It is going to be the square root of x plus the square root of y over the square root of x plus the square root of y. That fraction is still the same as the number 1. I hope you would agree with that. Those two factors cancel. And so that is really, truthfully, the number 1. A couple things I want you to note here. One of the biggest mistakes I will see in a mathematics course is that students will only multiply the denominator by the conjugate. And if you only multiply the denominator by the conjugate, well then you're not multiplying this fraction by the number 1. You're multiplying it by the number 1 over the square root of x plus the square root of y, which is going to change the size of this fraction. So you do have to keep all of that stuff in the numerator as well. Whatever you do to the numerator, you have to do to the denominator, and vice versa. All right. The second thing I want to note here is that you need to liberally use grouping symbols. I do see it very often that students do not use grouping symbols. If you don't use grouping symbols, this will often confuse you. Trust me, I taught for 15 years so far, and I've seen it enough times that students, they innocently write this denominator without grouping symbols thinking, oh yeah, I know that I'm going to distribute. But in reality, what ends up often happening is they get really freaked out. They're working on an exam and they've developed a bad habit of not writing these grouping symbols. And when they don't write those grouping symbols, they end up confusing themselves and only distributing this picture to those two items. Actually, they only distributed that last item, and that's it. And it ends up being incorrect. So be very, very careful. Use grouping symbols here. You're multiplying that entire denominator by its conjugate. Okay. Now, I do want to hop back here. I want to showcase something. In that list of advice or steps, I suppose, I don't know, that I wrote down earlier, I started with the fact that there are sometimes some fractions that you do have to rationalize numerators for. Second one was, in general, if the denominator only has one term, which isn't the case we're currently working on, we wouldn't bother rationalizing. And then the third one, once you've determined to rationalize, a second consideration of distribution comes into play. And here's where we're at with this problem. We've determined to rationalize the denominator, so therefore we've multiplied both numerator and denominator by the conjugate of the denominator. Now we have to consider, should we distribute things or not? And the advice with distribution goes as follows, and I'll hop back to the previous page to write this down. So we're back here on our advice page, I guess I'll call this, And once we've determined to rationalize, that second consideration of distribution comes into play. And the second consideration leads to two cases. Either you're given a fraction that doesn't have any variables, so it's just a bunch of constants. That would be, for example, this guy right up here. It's a fraction that has only constants within it. You don't see an X or a Y or a happy face or a Z or whatever. So in those cases, you should distribute everything and then simplify. So you're doing conjugate multiplication to both the numerator and the denominator. You would do that multiplication to both the numerator and the denominator and distribute things through and clean things up and do a lot of mathematics in the background to simplify, okay? On the other hand, if the fraction does contain variables, which is the case we're dealing with in this little sub-example I'm doing, only distribute the conjugate factors. This is critically important in calculus. And that's because when you distribute the non-conjugate factors, you end up really making the problem incredibly messy and hard to see that things cancel. So in this case, I'll distribute the conjugate factors. And when I say the conjugate factors, I mean this guy and this guy. I'll go ahead and do that distribution. If up in the numerator, and this is an if because it's actually not true in this case, but let's pretend that the numerator had x plus y up there for some reason, okay? These two expressions or factors are not conjugates of one another, so do not distribute them. That is what I'm saying. If you have variables, you should distribute the stuff that is conjugate. So the two factors that are conjugate, distribute that through and clean that up. But the non-conjugate factors, do not bother distributing those. And I'll see if I can create another example, because I think the one example I have, the official example I have in this problem, will not cover that scenario. So let's go ahead and just do this here. It's something beautiful and magical that happens. In the numerator, well, you know, that's just 1 times the square root of x plus the square root of y. In the denominator, and by the way, you don't have to write that as 1 times that. You could just write x, square root of x plus square root of y. In the denominator, we have square root of x times the square root of x, which is x. And that is from the law of exponents, right? The square root of x is the same thing as x to the 1/2 by definition. And then we know that if you take the square root of x and multiply it by the square root of x, that would be the square root of x squared, which, by the way, technically is the absolute value of x. So I'll go ahead and write that in here, and we'll talk about that a little bit later. But the reality is, when you take the square root of a number squared, it returns the absolute value of that number. Again, that's not necessarily important for our example right now. So I'll talk about that in a later series of videos. But for right now, because x has to be positive anyway, because you're taking the square root of it, this will just return x itself. If I wanted to wrangle in this little definition, I could say the square root of x times the square root of x is x to the 1/2 times x to the 1/2. And we know from the law of exponents, for one of the laws of exponents, that like bases multiplying means that their powers add. And I am so zoomed in that my handwriting's blocky. Sorry about that. It's still going to be blocky because I only zoomed out, but that's okay. So this will be x to the 1 or x to the first power. So that's just a reminder of your laws of exponents. So when we have the square root of x times square root of x, we get x to the first. Then when you get square root of x times square root of y, we'll have a positive square root of x times a positive square root of y. And then we have this negative square root of y times a positive square root of x, which by commutativity of multiplication can be written as negative square root of x times square root of y. And finally, negative root y times root y is a negative y. Again, that's because root y times root y is y itself. And this is the beautiful thing about conjugate multiplication, is that things will cancel. We have a positive square root of x times square root of y, and that will cancel a negative square root of x times square root of y. And that's why it's called rationalizing, because you turn these numbers into non-radical, or these pictures, I should say, into non-radicals, which means they might be rationals. We don't know what x and y are, so we have no clue if that's actually going to be true. But there we go. That's the completely simplified form of the original statement, 1 over the square root of x minus the square root of y. This is the rationalized form of that. Now, as a review, I usually don't throw in a bunch of definitions or silliness like that because you've seen this stuff so many times in the past that there's no need for me to write out and teach this. But I do want to mention, as an aside here, the conjugate is defined to be such that a plus b is the conjugate of a minus b, and vice versa. So a minus b is the conjugate of a plus b. This is just by definition. This is how we know what a conjugate is. We just define it to be this way. It doesn't have to be that you're working with radicals to have a conjugate. So for example, a very famous subset of conjugates are going to be with imaginary or complex numbers. So like 3 plus 2i, its conjugate would be 3 minus 2i, that type of thing. And if you don't know complex numbers, that's fine. It's not where we're at right now in at least the course that I teach. Now I want to head back over to this page. I want to mention a couple things before we move into the official example. One, we've already talked about how to rationalize a denominator. I didn't really focus too much in on what if your denominator has a single term like that guy right there. Would it be wise to rationalize that denominator? I'll just say it right now. No, it wouldn't be wise. The only reason why you learn to rationalize denominators for single-termed denominators is because you didn't have a calculator, essentially. That's why rationalization originally started as becoming en vogue, I suppose. Maybe I should say it that way. And just to really justify that statement, way back when there were no calculators and you had to figure out an approximation for 1 over the square root of 2, you used to have to go to a table of approximations for radicals, and or a book that had an approximation of radicals, and there would be an approximation of the square root of 2 in there, just like there would be an approximation for the square root of 3 and the square root of 5 and square root of 6 and so on and so forth. You'd have these long decimal digit approximations. It was essentially like a calculator, but in written form. So you turn to page 10 and there you have the square roots, right? And you go to square root of 2, 3, 4, so on and so forth. Well, not 4, but so on and so forth. Anyhow, square root of 2 in that book would be something along the lines of 1.41421, and we'll just round it 214. That's a rounded version of that. It's not exactly equal to that because this is irrational number, so it goes on forever with no pattern. But we'll go ahead and just stop it at 4. Actually, maybe I should just write 3 ... And you would do division, just like you would way back when in elementary school, long division, right? You'd have 1.0000, and you'd have a bunch of zeros here, right? And if you remember in elementary school, when you did this type of division, if you had a decimal dividing into, or a decimal number dividing into a constant or a integer like this, you would have to move decimal places. And so let's say that we just want to truncate this or round this square root of 2 to a 1.414214, then you would have to do this division by moving that decimal place 1, 2, 3, 4, 5, 6 units over. And so you'd move this decimal place 1, 2, 3, 4, 5, 6 units over. Go ahead and just do that. There we go. Keep that. Remove this. Oops, but I didn't mean to remove that 4. There we go. And then you'd ask yourself, well, how many times does 1,414,214 go into, what is this? 1 million, right? And you'd say, oh, it doesn't go into 1 million at all. Great. And then you would multiply by 0 and so on and so forth. And you'd have this very long process. It ends up being an incredibly long process. So then you ask, well, how many times does it go into 10 million? Because that would be this place, right? Oh, how many times does it go into 10 million? And you would find out that it goes in about 7 times. You'd multiply that 7 times this whole entire thing, and you get this really nasty number. So, rationalizing denominators comes to the rescue in that very special circumstance. Because if you had started this problem 1 over the square root of 2 and said, before I do my long division, I'm going to go ahead and rationalize the denominator by multiplying by the square root of 2, which is not technically, if you think about it, the conjugate. Well, okay, it is the conjugate because that denominator is square root of 2 plus 0. So the conjugate of that is square root of 2 minus 0. And therefore, multiplying by the conjugate just means multiplying by root 2. So both numerator and denominator. The numerator becomes the square root of 2. The denominator becomes a 2. Remember, these two numbers, 1 over root 2 and root 2 over 2, are identical as far as magnitude goes. But what's nice about the long division in this case is that it becomes much, much easier. 2 goes into 14 7 times. 7 times 2 is 14. Subtract, right? And then you could bring down the 1. 2 does not go into 1. So you're going to bring down this 4. 2 goes into 4 7 times. Notice I have 3 decimal digits of accuracy already. And I did not, it's really fast computation if you rationalize the denominator. Right? Then you would bring down the 2. 2 goes into 2 once. So now I have 4 decimal digits of accuracy very quickly. So anyhow, that's why rationalizing denominators was en vogue or popular, is that you didn't have calculators. And so you needed to be able to do speed up your computations. And the one way you would do that is rationalizing denominators. These days, there's no need for that. Finally, we're going to look at, and when I say finally, I mean in my made up examples here, because I have one official example next. But finally, what we're going to do is just showcase why that consideration of distribution comes into play. So let's take this example here. You notice there are variables in this, and somebody says, I need you to simplify this. When they say simplify, that includes or wraps into it rationalizing denominators, if you can do it. So I'm going to go ahead and rationalize denominators here. I'll grab that entire numerator and that entire denominator, and I'll multiply both of them by the conjugate of that denominator, which is a square root of x minus a square root of y. Again, you do that action to both numerator and denominator. You're essentially multiplying by the number 1. And that consideration that I mentioned earlier is that when you have conjugate multiplication, when you decided to multiply by conjugates, if you have variables involved, only do distribution on the factors that are actually conjugate to one another. Don't do distribution on the factors that are not conjugate. So don't bother distributing out that numerator. And this example will showcase why. So in the numerator, I will leave that as a completely undistributed statement. So it looks like you're really not doing any mathematics. You're just attaching a picture to a picture. In the denominator, that distribution is going to give me an x minus y. You can double check my mathematics there, but it is true. This conjugate multiplication always leads to a difference of squares. It'll take this first object and square it minus the second object and square it. That's all it will do. So it'll be an x minus a y. You can double check my statement, but it is very true. That is actually what happens. But once you get down to that quick statement, notice this picture in the denominator is identical to the picture in the numerator. Let me highlight them. So the picture in the denominator is identical to that factor, which is a picture in the numerator of x minus y as well. And so they will cancel. In other words, you can divide both numerator and denominator by x minus y. And when you do that, you're left with a beautiful square root of x minus square root of y. Notice that that statement is significantly easier to look at than the initial statement, which was x minus y over root x plus root y. But had you distributed out that stuff in the numerator, you would never have known that things cancel beautifully. So this is why I tell you, if they're non-conjugate, don't multiply them out when they involve variables because you need them factored so you can see what cancels. It'll be very, very important as you move into calculus to follow this advice. So as our only official example in this video, we are going to simplify this very nice non-variable expression. So this is going to just involve a little bit of order of operations and patience. When you're handed an expression like this, you should write equals first because you're changing that out for something equivalent. And then you go through and focus on numerator first. So in this case, let's take a look at these two radicals right here. I'm going to ignore everything else. And you are more than welcome to do multiple things at once, but I'm just doing this as a review. And in a review, I like to be very careful with my steps so that you can see the logic that you might have been missing from previous courses. So let's go ahead and do this. We already know the square root of 81 is 9, so that is not a big deal. But the square root of 27, what we're going to do first is rewrite 27 as the product of two numbers, one of which we can take the square root of. So I can take the square root of 9. So I happen to know 9 times 3 is 27, and I can take the square root of 9. So I'm going to rewrite that square root of 27 as square root of 9 times 3. And then square root of 81 we know is 9. And then another thing you need to note, by definition, the 3 to the 1/2 power is the square root of 3. So minus square root of 3. All right, so far so good. Then in our next step, and by the way, that first step, if you're labeling kind of the actions you did, you basically factored 27 in that first step. Next step, we're going to take the square root of 9 and move that out front. We're still left with a square root of 3 inside. So square root of 9 is 3. And then we cannot take the square root of 3 easily. So we just rewrite that in exact form as the square root of 3. Otherwise, everything else remains unchanged. Now, I sort of hand waved a little bit here. There's a property that we're using, and I'll write it over here. If A and B are both positive, then the square root of A times B is the same thing as the square root of A times the square root of B. In other words, you could break apart radicals as long as the radicands, the factors of the radicand, are positive. So I just split this radical apart into the square root of 9 times square root of 3, and I ran the square root of 9. And then I would, again, still focus on that numerator and notice there's nothing else you could do. They're not like terms. I suppose you could factor a 3 out, but I'm going to let you know right now, that's not actually going to help us out if we do that. So I'm not going to bother factoring out a 3. Again, you could totally do it. I'm just not going to. So then we move our focus down to the denominator. And that denominator also has two unlike terms, so they cannot be added or subtracted from one another. And there's no simplification you can do. So we're kind of stuck with this fraction sitting out front. However, we can rewrite that square root of 3. We can get these two fractions to have the same denominator. So let's go ahead and do that move. At this point, by the way, there are two directions you could go. You could either rationalize the denominator of this first fraction, or you can go ahead and rewrite the square root of 3 as an equivalent fraction with the same denominator as the first fraction. And I'm just choosing to go that route for no other reason than I want to. So I'm going to go ahead and take that square root of 3, and I'll attach a 9 minus root 3 to its numerator, and a 9 minus root 3 to its denominator. And you can see that both of these fractions now have the same denominator, and you can group them together beautifully. So I will go ahead and do that. So all I did was multiply in this step. I multiplied that root 3 by the number 1, a very special form of it, but a special form so that I can get a like denominator. So this fraction becomes a single fraction. I should say this difference of fractions becomes a single fraction. 3 root 3 minus 9 minus root 3 times 9 minus root 3. And this is all over 9 minus root 3. At this point, you just jump into that numerator and continue cleaning it up if you can. So I'm going to go ahead and do that here. We have 3 root 3 minus 9, and we're going to do a distribution. Negative root 3 times 9 is a negative 9 square root of 3. And then negative square root of 3 times a negative square root of 3 is a positive 3. Downstairs, we still have, oh, it's too long. Sorry about that. Downstairs, we have a 9 minus square root of 3. Again, in the numerator, just combine like terms. I'm going to write the the non-radical term out front. So negative 9 plus 3 is a negative 6. And then 3 root 3 minus 9 of those root 3s gives me a negative 6 of those root 3s. This is all over 9 minus square root of 3. And this looks to be pretty awesome, like that we're almost done. Or if you're not asked to rationalize the denominator, you're completely done. But let's go ahead and go one step further and rationalize denominators. Now, I do want to mention here, there are several tactics that people will use. Probably one of my favorites is to factor first. So in that numerator, I can factor out a negative 6, and I'm left with 1 plus a square root of 3. The only reason why I like to do this first is because it reinforces the algebra you've learned in the past. It also kind of makes a conjugate or a multiplication much easier, I think. Just my opinion, though. All right, let's go ahead and now rationalize the denominator by multiplying both numerator and denominator by 9 plus the square root of 3. Again, it was not explicitly stated for us to rationalize the denominator, but I'm just going to go ahead and say, let's just do it. Now, if this statement, this fraction if this contained variables, I would say do not distribute out the numerator. However, this statement does not contain variables, so I'm going to distribute everything. It's just a good idea to do that. So let's go ahead and start with the numerator. I'll leave the negative 6 out front just because that makes the mathematics a little bit nicer. Leave the negative 6 out front. 9 times this 1 gives me a 9. Let's see. Root 3, I'm going kind of backwards. Maybe I should go this way. 1 times 9 gives me a 9. And then 1 times that square root of 3 gives me a positive root 3. And then I have a positive root 3 times 9. Well, that's another 9 root 3. And then I have a positive root 3 times a positive root 3, which is a positive 3. Downstairs, since that is a conjugate multiplication in the denominator there, I will go ahead and just remind you that when you're multiplying conjugates, it's the square of the first thing minus the square of the second. So this would be 81 minus 3. Now we go ahead and continue cleaning up. This will be a negative 6. I leave that factored out there for a very special reason. And then times the quantity. Let's see, 9 plus 3 is 12. And root 3 plus 9 more of those root 3s is a 10 root 3. And downstairs we have a 78. And as I mentioned, I left that negative 6 out front for a very special reason, because 6 goes into 78. Let's see, 13 times. So I'm going to go ahead and cancel that 6 into that 78. So I have a negative 12 plus 10 root 3 all over 6 went into 78 13 times. And this is completely simplified. Nothing else you need to do here. Lots of little steps in there, but it's very important that you're able to follow the logic as we move through the course. These skills, by the way, are critical for calculus. Believe it or not, rationalizing denominators and rationalizing numerators, they end up being incredibly important skills as you move into calculus. And because you're in college algebra or that level of course, this skill you need to work on.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.